Okay, so let's finish up section 11.2. So yesterday we looked at adding up all the terms in a finite series. In a finite series, they always add up to something because you have a certain amount of things you're adding. It doesn't go on forever. Okay, well, today we're going to look at an infinite series. Now, obviously, we can't add up infinitely many terms, right? So we've got to come up with a way to do this so we don't have to add up infinitely many things. At least get an idea if we were to add up infinitely many things, what it would approach. Okay, kind of like an asymptote. Okay, so sometimes when you add up all the terms in an infinite series, they do add up to something, okay, or approach something. Sometimes they don't. Okay, it depends on what kind of series it is. And that just by itself can be hard to determine. All right, whether or not your series adds up to something or doesn't add up to something. Forget what it actually adds up to, just to find out if it even could add up to something. That can be tricky. Okay, but it's something you can study in calculus. Okay, so here's your notation for an infinite series. Okay, the only difference is the stopping point at the top of the sigma. It's not a letter. Okay, it's not a fixed point. It's infinity. Okay, it goes on forever. Remember this bottom number, that's called your index. On the right-hand side, that would be your sequence. That's the formula that's generating the terms you're going to add up. Right? I already mentioned this idea. So you can't really add up an infinite number of terms directly. It's not possible. Right? So we're going to have to look at kind of a way around that, kind of like an asymptote idea. Okay, so if you try to add up an infinite number of terms, okay, and there's a number s, such that when you graph the line y equals s, this line is a horizontal asymptote for your sequence of partial sums. All right, so we're going to look at a sequence of partial sums. And maybe the first partial sum, I'm just going to make up an example, is like 4. Okay, the next partial sum is 6.5. Okay, the next one is 6.8, then 6.9. Then 6.93, then 6.98, 6.99. Okay? As we look at that sequence, if we were basically, in this case, to look at the number 7, okay, the numbers I was just saying were getting closer and closer and closer to 7. So what we'd do is we'd graph what we think the asymptote is. Okay? We could use a formula, which I'll show you in a little bit, and see if our sums actually are getting closer and closer to 7 when we graph them. That's the basic idea. So we'll use a formula, we'll graph our partial sums, and see if it looks like it's approaching a number. If it does approach a number, then we say that this sequence converges. Okay. Anytime you add up a bunch of terms and it approaches something, that's called convergent. And what would it converge to? Well, it would converge to s. That's the number that would be our horizontal asymptote. Looks like it's getting closer and closer to. Okay, any question on that idea? Okay, it's kind of confusing, I think, to just write it in words. It's very simple if you just look at it in a picture. It's not too hard. Okay, so what we're going to do is we're going to look at what happens as n goes towards infinity. All right, so practically what we might do is look at like the 5th partial sum, the 10th partial sum, the 20th partial sum, and if it's going to converge, we're going to see it converging usually pretty quickly. Definitely by the 20th partial sum. Right? And we can just use the table on the calculator. We are not going to have to add up to find the 20th partial sum. Okay, the calculator will tell us on the table. Okay, so as n gets bigger and bigger and bigger, our nth partial sum is going to approach some number, s. And that's going to be the sum of our series. All right. So this is kind of how we're going to cheat and get around that idea of adding up infinitely many things. Okay, so an infinite series isn't really a sum. what we're really doing is we're going to look at a sequence of partial sums. We're just going to look very, very, very far down the sequence. Okay? And the farther we look down, the better of an idea we're going to get what it's approaching. If you look at the first or second partial sum, you're not going to know what it's approaching. You got to look way out. Okay? Look way down at your sequence of partial sums. Okay, and just to make it clear for anyone who wasn't here yesterday, this is how we write partial sums. Okay, how you'd calculate each term in the sequence. Let's say you had a sequence A. Okay, this one basically would just be the sum of the first term. This one would be the sum of the first two terms. This one would be the sum of the first three. And S4 would be what you get when you add up the first four terms in your sequence. Okay, so as we get further and further down that sequence, each term is generated by adding up more and more and more terms, essentially approaching infinitely many. Any question on that idea? How you find your partial sums? We kind of did that yesterday. Okay. All right, so here's again the notation for an infinite geometric series. Okay, we're going from 1 to infinity, and we're starting out with our first term times r, and I might have used n when I gave you the formula originally. Generally, our book uses k when they talk about a series. Okay, the variable is not overly important as long as you're consistent. Okay. All right, so in a geometric series, you've got your first term, and then to get to the next term, you'd multiply the first term by r. To get to the term after that, you'd multiply that term by r. So the next one would be a sub 1r squared, and then you'd multiply by r again. A sub 1r cubed. Okay? All the way till you get up to a sub 1r to the n minus 1, but now it keeps going after that. Okay? There's no end to it. Normally, we would end right there. All right, so let's look at this. Let's go back to yesterday, but I think this is one that we looked at yesterday. It was one of the last problems. Okay, let me see. Let's see, is this the same one? Okay, so my first term is 2. Problem we did yesterday, the first term was 2. And what am I multiplying by each time?
1/3.
Yeah, I'm multiplying by 1/3. That's exactly what this one is. Okay, so this is really the last problem we did yesterday. Okay, in order to evaluate this, we're going to graph it. Okay, so to graph it, we have to make sure we know the notation. Okay, what I'm going to do for now is I'm just going to use the same formula we had yesterday. I'm basically going to fill in a sub 1 and r and look at what that picture looks like. Now, this is the formula for a finite geometric series. We're doing infinite. So what we're going to do is we're going to look at what happens when n starts to get really, really big. Right? We'll go down in the table and see what happens. And if it looks like we're approaching something, we'll write that down. So let's type that in. Trickiest thing is you got to be careful with your parentheses when you try to type this in. Right, so I'm going to put the 2 at the very end. So I'm going to put 1 minus r. Okay, I can't use the variable n. I have to use x when I graph it. Okay, so that's 1 minus r to the n. That's my numerator. Divided by, in the denominator, it's 1 minus 1/3. Okay, in this case, r is 1/3. So you know what, just put, you could write it as 1 minus 1/3, or you could just put 2/3. Just put 2/3. And now all of that is multiplied by A1. A1 is in front. Okay, so I'm just put parentheses around the whole thing. Maybe. We can get there. Okay, so any questions how I typed that in? Now, if I just wanted to look at a specific partial sum, I could let x be 4. If I just wanted to know the fourth partial sum. Okay, or let x be 5, or let x be 6, whatever I want. I'm letting it be a variable, so that way I can go second table, and I can look at all of these. Okay, so I already did some of them out to save time. Okay, but this is how you'd add up the first 4 terms. 1 minus 1/3 to the fourth, divide by 2/3, and you get 2.96. Okay, let's get rid of these, and then we'll check our table. We'll be back in about 5 minutes. All right. So there's our fourth partial sum, 2.96. Okay, fifth partial sum. It'd be 2 times. And the only difference would be change your exponent from a 4 to a 5. Okay, so we don't have to do all that out. I already did it. Comes out to 2.9877. Okay, so we can already see pretty quickly, it looks like it's approaching something. Okay. Here's our sixth partial sum. Okay, 2.9959. What does it look like it's approaching? Andrew? 3. Okay, so if you want to see, go down maybe to your 15th partial sum. Okay, at this point it looks like it's 3. It's never going to reach 3. Okay? This graph is kind of coming up from below a horizontal line, y equals 3. And it's coming up closer and closer and closer to it. Eventually, the calculator is going to run out of decimal places. Okay, it can only go to so many. So if you put in a high enough partial sum, it's going to say that it's 3, even though it's not. It's really 2.9, which is more decimals than the calculator can write. All right, let's graph it. Okay, we think there's a horizontal asymptote at 3. Okay, so let's go zoom 6. Okay, here's our partial sums. Here's our asymptote. Looks like it's almost crossing it, but it's not. The blue line is just getting closer and closer. Okay, also, another thing that doesn't make sense here is the domain it's connected. Okay, really, these would be individual dots. Okay, that's how you want to think of it. There's a 4th term and there's a 5th term. There's no 4.5 term. There's nothing between the 4 and the 5. Okay. In fact, if you try decimal on your calculator, see what happens. Okay, it's giving you a number, but that's because this is just a function. Okay, it's not thinking of it in terms of a sequence. 4.5 would never be a value you'd plug in for the exponent, right? So remember, it should really be dotted. Not connected. Okay, so any questions on that? Okay, so clearly an asymptote in that problem. It looks like it's approaching 3. Okay, so we already visualized the sequence. That's what we just did. Okay, that's the graph we did. Remember to focus on the positive integer values of x. Don't look at negatives. Don't look at decimals or anything in between the integers. And as x starts to get really big, approaches infinity, that's a pretty good approximation of what infinitely many terms would add up to. Okay, so find the sum using a graphical approach. We already did that. The sum converges to 3. Okay, so that's what this adds up to. It adds up to 3. Any questions on that? All right. Okay, let's look at this one. Let's just write down our first term. Let's write down r. And then we'll graph it, same way we did the last one, and see if we can figure it out. Okay, what's my first term here? And if you're not sure, just let k equal 1, plug it in, and you'll see what the first term is. Josh?
4.
4. Yeah, first term is whatever the number is in front. 4. Okay, what's r? What's that going to be here? Yeah?
3.
3. You're multiplying by 3 each time to get the next term. Okay. So if you were to write your terms out in this sequence, your first term would be 4. Then the next one would be 4 times 3, which is 12. The next one would be 12 times 3, 36, and so on. Right, so let's fill that in. We won't even graph it yet. Let's just take a look at it. Okay, so we have 4 times 1 minus 3 to the n, all over 1 minus 3, which we could just write as negative 2. Okay, before I graph it, any thoughts of what's going to happen to this expression as n starts to get really, really big? Well, what happened in, let's look at this one. Okay, so for this part, as n started to get really, really big, what happened to just the part that I'm circling each time? 1/3 to the 4th power, 1/3 to the 5th power, 1/3 to the 6th power. Yeah? Yeah, this part was getting really, really small. What was this part approaching? Yeah, this part was approaching 0. Okay. What about this thing inside the parentheses makes it approach 0? Why isn't it getting bigger and bigger? Yeah?
It's less than 1.
It's less than 1. If you take something less than 1 and keep multiplying it by itself, your number gets smaller and smaller. All right, so let's go back and look at what we have. Okay, what's going to happen to this part as n continues to grow? Yeah?
It's going to get really big.
It's going to just get really, really big. This part's not going to keep getting smaller and smaller. So now what's going to happen is this is going to grow forever. You're going to have 1 minus a huge number, and you're going to multiply by 4 and divide by negative 2, which really isn't that important. Okay, this is the whole problem right here. So if we try to graph that, let's see what happens. So let's get rid of our asymptote. This time we have 4 minus, it's just 3 to the x, and it's divided by negative 2. Okay, you know what? Don't even graph it. Just go to your table. Okay, so your first number is 4. If you add up the first two numbers, well, we said the first term was 4, the next term is 12. If you add 4 and 12, you should get 16. Okay, the next term is 36. So if you take 4 and 16, I'm sorry, if you take 16 and then add 36 onto it, you get 52. All right, so it's growing very quickly, and it doesn't look like it's approaching a number. If you go to the 10th partial sum, it's not converging. All right, so this sum is divergent. Okay, it doesn't add up to anything. So the sum approaches infinity. Okay, and I think I have the name for that on the next page. Yeah. Okay, so this sum approaches infinity. And when you start to get familiar with these, you can look at it pretty quick and figure out, okay, he has a number bigger than 1 raised to a power, it's going to approach infinity. Between 0 and 1, it's going to converge. Then you can find what it converges to, graphing it, or using this formula. Or actually, I'll give you an even simple formula. I didn't actually show you the graph, I just showed you guys the table. But it's going to go off the screen pretty quickly. Okay, very, very quickly, it's just heading up. Okay, so since it's heading up, it's not approaching any values. Okay, there's no horizontal asymptote. We say that this series diverges, okay, or it's divergent. Right, so sometimes a geometric series can converge, sometimes it diverges. It depends. All right, so I don't think we really need to do this, but they give you an activity in your book to try. Basically, taking the equation we just did, playing around different values for r, and seeing when it converges and when it diverges. Okay, let's just write down what you guys think. If r is 0.8, think that would converge or diverge? Yeah, that'll converge. How about if r is 0.9? Think, Michael?
Converge.
Yeah, that'll converge. Okay, now a slightly different question. Which one will converge faster? Think if r is 0.8 or if r is 0.9. Basically, think about if you start raising these numbers to powers, which one is going to get smaller faster? Yeah? Yeah, 0.8. If you multiply 0.8 times 0.8 times 0.8, that's going to be a smaller number than 0.9 times 0.9 times 0.9. Right? So the smaller your number is between 0 and 1, the faster it converges. Okay, that's something we could take a look at. Okay, let's just make up a sequence. First term is 4. And let's let r be let's do 0.9. Okay, divided by would be 1 minus, let me just insert 0.9. Okay, so I just made r 0.9. All right, so if you go to your table, okay, it is converging. Okay, it still looks like it's growing pretty quickly. Okay, still some jumps in there, but let's go all the way up to like 50. Okay, we're at 39, we're up to 75. Now 39.9. My guess is it's probably going to converge to 40. Okay, try 250. Okay, so it's converging to 40, but it's very slow. Okay, so if you graph this one, you need to set your window probably out to at least 100 to get a good idea that this one's converging. So let's set that at 100, and we know it converges to 40, so let's go up to 50. Okay, so it takes a while to get there. Okay, remember, this is growing all the way to 100 now, so it's a lot bigger window. Okay, versus if we did 0.8. Okay, you know what? Let me just take this graph, put that there. Now let's change it to 0.8. Okay, or even something. I want you to see a bigger difference. Let's do like 0.5. Okay, so this will converge a lot faster. It's converging to a smaller number, but my point here is that's not what I wanted. Let's try again. Well, just look at the two like that. So it's going up, and it almost looks like it takes like a right turn. Okay, it converges very fast. Okay. What about if I did 1.1, 1.2? What do you think is going to happen with those? Yep. Yeah, these are going to be divergent. Okay. This one is going to diverge slowly. It's not going to go quickly, because if you keep multiplying 1.1 times itself, it gets bigger, but it doesn't get bigger very fast. 1.2, it's also divergent. So the further your number is from 1, like 10, 20, really, really big R value, the sharper it's going to curve up. Okay, in this class, we really don't describe the speed at which it converges or diverges. We just say it's one or the other. Okay. Any questions on that? Right, so the idea, I just kind of summarized it for you. If your absolute value of r is less than 1, that's when it'll converge. If you take any number between -1 and +1 and multiply it together infinitely many times, except for 0, it will converge. If you throw 0 in for r, that kind of messes everything up, because 0 to any power is just 0. Okay, you always get the same result. If you always get the same result when you do r to the n, and then r is a constant and a sub 1 is a constant, you basically get a horizontal line. You wouldn't have this converging. It would be different. Okay, so let's see what happens when it converges. Let's see if we can come up with a simpler formula. Okay, so the formula we did yesterday was for a finite geometric series. Now we're going to look at the formula for an infinite geometric series, as long as it fits this condition. Okay? So again, I want you to focus just on this part. I already asked this earlier, but what happens to that part? If r is between -1 and 1, and n approaches infinity, what does what I circled approach? Justin? So if r is somewhere between -1 and 1, and you raise it to an infinitely large power, what happens to it?
It's between -1 and 1.
Yeah, not including -1 and 1, strictly between.
Then it will converge.
Well, what does this approach? It actually approaches this part that I circled, approaches a number. Give me a number between -1 and 1.
0.
Not 0. Try again. Can't be 0 because that whole thing I just explained. You'd end up with a constant, it'd be a horizontal line.
1/2.
1/2. Okay. Give me a power to raise that to.
28.
28. What's that approaching? It's in scientific notation, but it's basically 0.08 times, or 9 times, and then a 3.
0.
Yeah, it's approaching 0. Take any number that's absolute value less than 1, raise it to an infinitely large power, this approaches 0. Okay, so plug that into your formula. How could I simplify that?
1 over.
Not quite. There's nothing I can do with that denominator. Yeah, the denominator is going to stay the same.
So it's going to be just 1 over 1 minus
There's something else there too we forgot about. That I
sub 1 over 1 minus r.
Yeah. Basically, if you want to think of this as a fraction, the top becomes 1. Multiply a sub 1 times 1. Okay, the numerator is just a sub 1. That's all that's in the top. And in the denominator, it's 1 minus r. That's the formula for the sum of an infinite geometric series. Okay, it's all based off of the formula we did yesterday, the sum of a finite geometric series. All right? So this term that we circled basically becomes not important at all. It approaches 0. So we just focus on the other part. Okay, any question on that formula? So all we've done really is talk about geometric series. We did finite geometric series, infinite geometric series. How come I'm not talking about arithmetic? Why can't we find the sum of an infinite arithmetic series or sequence? We could find the sum of a finite arithmetic. You can find the sum of a finite anything because it has a stopping point. Why not an infinite arithmetic sequence? Yeah?
Because there's no end to the numbers that you need to add. So to have a sum, you need a defined range of numbers to add up. But you don't have that in an infinite because you've got never-ending series of numbers.
But I have a never-ending series of numbers here, too. I'm adding up infinitely many things. There's no end to it.
Yeah, you're using a variable to represent it.
Okay, I could use a variable, too, with arithmetic. Because this is never-ending. It goes on forever, adding up infinitely many things. But there's something about the things you're adding up that's different than an arithmetic sequence.
The arithmetic has no asymptote that it approaches?
Okay, how come? Why couldn't it ever approach an asymptote?
Because there's no multiplication involved, it's just adding onto another number repeatedly.
Right. With an arithmetic sequence, all you're doing is adding the same number each time. What you're adding, your terms are never going to start to get smaller and smaller. They're always going to get bigger and bigger and bigger. So if the terms in the sequence are getting bigger and bigger and bigger all the time, if you add them up, the sum is going to get bigger and bigger all the time. Okay? It's never going to approach something. The only way infinitely many terms can actually approach an answer when you add them up is if the terms start to get smaller and smaller and smaller each time and approach 0. It will never happen in an arithmetic sequence. That's why we're not talking about that. Okay, any questions on that? All right. All right, so I'm asking you to find the sum. First thing you should always check is he asking me to find the sum of something that doesn't even converge? Generally, I'm not going to ask you to do that. But can anybody look at that and tell me, does it converge? And if it does, tell me how you know. And then try to find the sum on your own after.
Yes, because because R is less than 1.
Yeah, R is less than 1, so this is definitely going to converge. All right? And it's an infinite geometric series. Okay, so try use the formula we just had on the other page. You don't even need to graph it now. Just use the formula we circled. Write down your first term over 1 minus R. Okay, and see if you can tell me what that's going to add up to. Okay, so try that on your own. All right. So as I walked around, most people had a good idea. Okay, what goes in the top part of the fraction? First term, a sub 1 over what goes in the bottom?
1/2.
How'd you get 1/2? Is it just this number? Because that in this case,
no, 1 minus 1/2.
Yeah, it's 1 minus R, which just happens in this time to come out to the same thing. Okay, so it's 1 minus R, 1 minus 1/2 is 1/2. Okay, and then 5 divided by 1/2 is 10. Okay? So that's what that series would add up to. All right, so I told you guys earlier that sometimes you just want to figure out whether a series is convergent or divergent. Okay, so there's all kinds of what they call convergence tests. Okay, some of them I think you guys would understand, especially if I can find one that says geometric somewhere. Geometric. There we go. All right, so a geometric series. Okay, the geometric series convergence test basically says if you have an absolute value of R less than 1, then the geometric series always converges too. That's the formula I just gave you. It's a sub 1 divided by 1 minus R. If R is bigger than 1, it diverges. Okay, so that test you would already understand. Right? Let's see. This test isn't too hard to understand. Absolute convergence. Basically, it says if the absolute value of your sequence converges, then the original sequence also converges. Sometimes it's just easier to work with absolute values, makes everything positive, than working with things that are always positive. This one's a little bit harder, alternating series test. Okay, that's when you have something oscillating, positive, negative, positive, negative. Okay, so I'm not going to get into that. Okay, integral test. This involves using calculus. Okay, so involves calculus to figure out if it converges. Okay, looking at limits. Okay, you guys maybe at least remember that from the beginning of the year. There's something you can do with limits. Again, that gets into some calculus. So you're not going to understand most of these tests. I'm just trying to show you that they're there. Okay, P-series, there's the ratio test, the root test, Taylor series, all kinds of different tests. Okay? Some of these tests can tell you if it converges or diverges, or if certain things happen, the test doesn't help you. Okay? So some tests, when you try to use them, you don't get a result. So if you tried the root test, okay, whatever that is, and you got a result that wasn't conclusive, you'd have to try something else. Okay? Okay, so all kinds of stuff about convergence in a series. All right. But you guys should at least understand that from what we've done so far. Okay, looking at partial sums. Okay, any questions on series? Okay, so that's pretty much all we're going to look at with sequences and series. Okay, tomorrow we'll start to look at the binomial theorem. All right, so the homework, you get a little bit of time in class to start. You get about 15 minutes. It's on page 601. Okay, I'd like you guys to try 21 to 22, 29, 30, 32. And then the rest is all. 33 through 35. 37 to 39, and 42 to 45. Okay, so we'll take a look at that tomorrow. Then we'll finish up our material for the week and then test on Friday.